this video we are going to discuss block diagram reduction rules. So why block diagram reduction is required means, so for example any control system is given in terms of block diagram. As I already told you, block diagram is the pictorial representation of each and every component in control engineering or control system. So if any control system is given in block diagram model, so that means indication of all components in blocks and signal flow and summing point and branch points like that. So if you are asked to find out what is the transfer function of the system, generally you know what is the transfer function of the system: output transform by input transform. So if you are having small block diagram, then that is very easy to find out the overall transfer function of the system. But whenever you are having so many number of blocks, so you can't estimate the transfer function or any other problems on that block diagram perfectly. That's why we need to reduce the block diagram. Reducing of block diagram is better because we can reduce the complexity of the structure, or we can find out the transfer function easily, we can find out gain easily. So for this, all these purposes, we are going to reduce our block diagram, but we need to follow some rules. These are some important rules that we must follow when we are reducing the block diagram. So this is the first rule: combining the blocks in cascade. When you saw two blocks in block diagram, no need to consider that two blocks as individual blocks. You can combine like this. So that means your block diagram, you can combine your series blocks like this, G1 into G2. You can multiply gain of each block and you can make that as a single block. So as you are having A here, so that is multiplied and the output is A into G1 into G2. Here also, so here you are having a signal A that is tending to a block with gain G1. So after passing through that first block, so the value from this block output is equivalent to AG1. This AG1 now passes to G2 and is multiplied with this block gain. So totally this block output is equivalent to AG1 G2. If you consider block like this also, you are getting the same output. Our intention is to get the same output. By taking individual block or combined block, you need to get the same output. If you are getting same output by taking the single block, what is the need to take two blocks? So that's why we can reduce this two individual blocks by combining the two blocks with multiplication. If the blocks, if you are observing the blocks in series, then you can combine by using multiplication. You can make them as a single block by using multiplication of gains. Coming to combining parallel blocks. So here, when you are combining parallel blocks, you need to observe here. When we can say blocks are in parallel, when blocks are like this with a summing point, blocks are like this, these two blocks are said to be in parallel. So how we can combine that blocks means, so here I can combine that blocks by using addition. Whatever the parallel blocks are there, that parallel blocks we can combine by using addition. Addition means, so just by adding the gains G1 and G2, you are going to get the same output. You can see here you given with A. For this block also you given with A. So this block output is AG2 and this block output is AG1. So this AG1 and AG2 are combined. So these are going to form AG1 plus AG2. For example, same input signal A is giving here. The output is A into G1 plus G2. So that is equivalent to AG1 plus AG2 only. You are getting the same output. If you are getting the same output with this single block, no need to take these two blocks in parallel with branching point, this summing point. So this is the reason why we require combining of blocks. With a single block we can do here. So now moving the branch point ahead of the block. Moving the branch point or moving the summing point ahead and before of the block will add a block into that path. If you are moving your branch point or summing point in next 2 points, we are moving summing point before and ahead of the block. So in that 2 cases also, so we are going to add extra block in that moving path. So you can see here, you can observe moving the branch point ahead of the block. That means, so this is before the block. If you want to move this block ahead of this block 1, then you need to add a block here in this path. Whatever the path is moving, in that path you need to add a block. So like this. So here you can see the equivalent is, so here you are having a block like this. So here you given A, so here AG, here you are having a branch point. If you want to move this branch point ahead of the block, then you need to consider 1 by G as your block gain. You need to add an extra block in that moving path. Whatever the path we are moving, this branching point we are moving. This is the branching point. This point we are moving to here. If you are moving that branching point, you need to add an extra block with gain reverse to the actual gain. So here you can see, so this is A. In this branching point you need to get A. So this is actual path AG. So in the actual path you got AG. So in this path you need to get A. So here this is AG, same AG you will get here. So AG into 1 by G you are getting A. So same A through this branching point you are getting. This is the reason why I am taking this reverse gain. As we are moving that branching point to ahead of the block, that block effect is there, which is not actually there. After moving, we are having that effect of the block. To reduce the effect of the block, I am using reverse gain in that path as a block. So I want to modify my block diagram like this. So the general path gain is AG, here also AG, the branching point value is A, here also I got A. So is there any case to move branching point ahead of the block? You can move like this. Similarly, moving the branch point before the block. For example, if you are having your branch point like this and if you need to do the reverse procedure, if you want to do the reverse procedure, that means if you want to move your branching point before the block, how we can do? So here, as I told you, when you are moving any branch point before and after the blocks, you need to add an extra block in that moving path. So here in the moving path, I added reverse of that gain, reverse of this actual gain. So here, when you are moving ahead to before, so here you need to add a block in this path with the same gain. So you can see here, so for example, if you want to move this branch point to before the block, then so here I am taking this block G and here I am actually having branch point, but I want to move this branch point to here. So I need to multiply this path gain. Here I need to multiply the reverse path gain, inverse of path gain. So here I need to multiply the actual path gain here. So now, for example, if you are having A here, through this also actual path also you are having AG, and through branch path also you are having AG. Here also you need to get this same. So here in the actual path you are having AG, and this path also you are having AG. So outputs are same. Outputs must be same. After changing the block diagram also, your inputs and outputs must be same. So this one of the important rule, moving ahead and before the block, moving the branch point ahead and before the block, and similar to that, moving summing point ahead of the block. So here we need to move this summing point ahead of this block. How we can move? So again same rule, when you are moving any summing point or branch point ahead or before the block, you need to add an extra block in that moving path. So in that moving path we need to add an extra block. So like this. So here this can be modified as G. So you need to consider gain G, and you need to consider, so you can see here this A plus B. So the summing point output is A plus B. This A plus B signal after passing through this block, that is equivalent to AG plus AB. So here also, so this is BG, so this is AG plus BG here, and here also after summing, so that is equivalent to BG plus AG. So like this we can move any summing point ahead of the block. So here when you are moving branch point ahead of the block, you are going to get 1 by G, but here you are going to get G. When you are moving summing point ahead of the block, you need to add the block with G. Here if you moved ahead of the block, you need to add extra block in that moving point as with reverse gain. So here similarly we are having moving the branch point before the block, like that moving summing point before the block. So if you want to move this branch point before the block, what we need to do? So here if you want to move, so here you can see this is AG plus B. So the output is AG plus B. You need to get the same output, AG plus B. So if you move this summing point here, that B is also entering to this block. So that block effect will be there on that B. To reduce that effect, I am going to multiply 1 by G in that B path. So you can see clearly how I can modify this block diagram means. So what I need to do, I need to move my point, before the block, and after this I need to get the gain. Here I need to give A, and here I need to give with 1 by G. Why? Because previously B is not going to enter through this block. When I move this summing point to here, through that summing point, after that summing point, you are having block. So that B needs to enter into the block, which is actually not there. So to reduce the effect of this block on B, so I am taking 1 by G here. Whenever you require negotiation of effect of a block on a signal, you need to consider inverse of that gain. So here this is B. Now by summing these two, so this is equivalent to A plus B by G. So after multiplying these two, I am going to get same thing, AG plus B. The output is AG plus B only here. So you are getting the same output. So now interchanging the summing point, we can interchange the summing points also. For example, if your summing points are like this, if you are having two summing points, that is like this, a b are summed here. So a plus b, the output is a plus b. This a plus b is subtracted with c. That means, so a plus b minus c will be the output of these two summing points. We can interchange the summing points. That means we can put this summing point here and we can put this summing point here. So like this. So if you are having the same structure with interchanged summing points, that will be like this. So same a you can give here, c you can give here, and after that you can give your b here. You can give this b here. So mention arrow marks, so that is better. It will shows the flow of the signal. So here also the flow will be like this. If I forgotten to mention the arrow marks also, you need to consider the arrow marks. So now here the result is from here a minus c. By adding a minus c with b, you are going to get the same, a plus b minus c. You are going to get the same. And now coming to splitting summing points and combining summing points. You are having summing point like this with a, b and c. The output is a plus b minus c. If you want to move this, if you want to change this, or if you want to split this into two summing points, you can split. So that means you can split like this. So if you want to split, so then you can split like this. So this is a and this is b. After this you can take another summing point and you can subtract your c. Up to here this is equivalent to a plus b. So here a plus b minus c. You can subtract like this. Splitting summing points, you can split your summing points like this, or if you want to combine, so you can combine like this, vice versa. So you can split and combine like this. If you are having summing points like this, you can combine like this. So here elimination of feedback loop. So how we can eliminate the feedback loop? So if you are having any feedback loop, then we can eliminate that feedback loop with feedback gain. This is negative feedback. You know the negative feedback system, negative feedback gain, you know the gain of negative feedback system. What is C of S by R of S? We already derived in the initial classes of control systems itself. What is the transfer function of that negative feedback loop? So here we can modify this by using a single block transfer function G by 1 plus GH. This is negative feedback gain. So this is R and this is C. H as feedback path gain, and we can make it as a single block by reducing that feedback loop as. In this video we are going to discuss block diagram reduction, one example related to block diagram reduction. So in this problem they given a bulk block diagram. So by this block diagram it will indicate a control system. So now we need to reduce this block diagram and we need to find out the transfer function of the system. So you can see, reduce the block diagram and find the transfer function of the system below. So this is the system given, control system given. So we need to reduce the system and we need to find out the transfer function. For example, at this instant, if you want to find out the transfer function, how we will find out the transfer function? We don't know C of S and we don't know R of S. If you are having any single block in between C of S and R of S, you can consider that as transfer function of your system. But you are having multiple blocks. When you are having multiple blocks in between your input and output, you can't say that particular transfer function. So here we need to make all these blocks, all these different blocks into a single block by using block diagram reduction method. Finally, that single block represents the transfer function of the system. Coming to the reduction, in the last class itself, we got some rules for block diagram reduction. So here you can see How we can redact? By observing itself, we are having some parallel blocks, we are having some feedback path, and we are having some series. Which path we need to reduce first? For example, if you want to reduce the series path, here this series element is in feedback with this feedback loop, so we can't. If you want to reduce this parallel element, so here also in this parallel path, if this feedback is not there, then definitely you can write G1 plus G2 plus G3. But here you are having a disturbance due to this feedback path. So because of this feedback path, you don't know the effect of this feedback on this gains. So that's why you can't do this parallel block reduction also. You can't do this first. You can't do this parallel block reduction first. So which we need to do? For example, if you want to do this feedback, so that's also not possible first. Why? Because so in this feedback path, this branch point is included. So we are having disturbance from other points. For example, here if you are having feedback loop, if you can reduce that feedback loop, then that will be better, but you are having branch point here. Whenever you are having branch point here, if you feel that branch point is an obstacle to you, then you can move that branch point to here. So we are having a rule to move any branch point to ahead of the block. When you are moving any branch point ahead of the block, then you need to multiply reverse gain of actual path. You need to add a block when block is not there. Already we are having block here, no need to add extra block. For this block gain, you need to multiply reverse gain of your actual path. So you can see I am modifying my block diagram like this. So here I am having a summing point like this R, and here I am having G1. Here I am having G1, and here I am having G2, my G2 like this, and here I am having another summing point like this. And here from here to here I am having a feedback path. So you can see what I need to do is, so I am moving this branch point to here. This is the first step I am doing. I am just moving this branch point to here to simplify this feedback path. So here I am moving this branch point to here. So the gain will be modified as G3 by G1. If G3 is not there, if you are having empty line, then you need to add a block and you need to write 1 by G1. If you are already having block, then for that block gain you need to multiply the inverse gain of this ahead block. So here I moved this point like this. So you can see now to reduce this feedback path I am not having any problem. So in the next step I am reducing this feedback path. So for this feedback path I am writing like this, and here if you observe these two are in parallel. So and these two are in parallel. So in the next step I want to do two things. One is I want to simplify my feedback path. I want to reduce my feedback path, as well as I want to reduce this parallel gains. So my resultant diagram will be like this. So here I reduced this feedback path. So you need to see which feedback that is a negative feedback. So G by 1 plus GH formula we need to take, as we are having G1. So G1 by 1 plus G1 into H. This will be the feedback path gain after reducing. So no need to take the summing point and these two open loop gain and feedback path gain. So in place of these three, we can replace this block. So I reduce the feedback path, and now my turn is to reduce these two elements. These two elements are in parallel. How we can reduce the parallel elements? By just adding the gains, we can reduce the parallel elements. So what are the gains means? G3 by G1 is 1 gain plus G2. So this is equivalent to G3 by G1 plus G2. So now my block diagram is reduced to like this. Now also I am not having single block. Now also I am having two blocks. So here you can see these two blocks are in series. So if these two blocks are in series, you can multiply the gains to make this as single block. So that means G1 by 1 plus G1 into H into G3 by G1 plus G2. So now the transfer function C of S by R of S is nothing but this gain. So G1 by 1 plus G1 into H. So multiplied with, so I am cross multiplying these two, G3, G2, G1 divided by G1. So I am cancelling these two. I am going to get my transfer function C of S by R of S is equivalent to G1, G2 plus G3 divided by 1 plus G1H. This is the transfer function of the given block diagram. This is the transfer function C of S by R of S. What we need to do when they are asking transfer function means we need to reduce the bulky block diagram into single block. So in between input and output, that block gain will represent the total gain or transfer function of the system.